Welcome to a tutorial on digital electronics, and in this tutorial I've just thought of discussing about the various types of flip-flops. Okay, so in this tutorial, or rather before coming into this tutorial, I just assume that the ones who are following it know already about the concepts of edge triggering and all discussed in our previous tutorials. So over here I just won't hesitate to introduce the JK flip-flop. All right, so there we go, the JK flip-flop. All right, so if you're just trying to figure out why is this flip-flop called a JK flip-flop, then I would say that there is definitely no valid cause of why its name is a JK flip-flop. So you don't need to bother about that, but for the time being, let's just delve into the working of this flip-flop. Okay, so before we go on to the details, let me just tell you that this flip-flop is an edge-triggered flip-flop. Okay, so that's an edge-triggered flip-flop, which is a JK flip-flop over here. Okay, so in this flip-flop, okay, if I just try and draw the circuit, so it would look somewhat like this. So here are the two NAND gates. I'll name them as gate 1 and gate 2. Okay, there are two more right over here, so I'd call them gate 3 and gate 4 respectively. Okay, now switching on to a different color, so these are the Q and the Q bar outputs. Okay, and there goes the inputs to this RS latch. Okay, since everything starts at the RS latch. All right, so these are the feedback paths, and now in this flip-flop circuit, a parallel path from the feedback paths feeds onto the gates 3 and 4 respectively. So there is the common connection between gates 3 and 4, and now there are two terminals branching out from gates 3 and 4 again. So these are referred to as the JK inputs. Okay, now from the common connection of the two gates 3 and 4, okay, here we have a circuit that is known as the pulse transition, okay, detector circuit. All right, so there we go. Here's the pulse transition detector circuit, and over here we would apply the clock signal. So now what this pulse transition detector circuit does is that it basically detects the clock signals, or rather clock pulses edges. So that's why it's an edge triggered flip-flop. Okay, so now this flip-flop, being an edge triggered flip-flop, could be triggered either on the positive or on the negative edge of the clock, or rather, to be specific, on the positive and negative edges of the clock pulse. Okay, so depending upon that, there are two types of flip-flops possible. Okay, one is the positive edge triggered JK flip-flop. Okay, so let me just first write it down: positive edge triggered JK flip-flop. Okay, and the other is the negative edge triggered JK flip-flop. Okay, so depending upon the two types of flip-flops that could be possible over here, we will have two different types of logic diagram representations for both of them. So if this is the logic diagram of a positive edge triggered JK flip-flop, okay, then it would look somewhat like this. Okay, here's the clock. Now notice the triangle right over here, the clock input. This basically shows that this flip-flop is an edge triggered flip-flop. Okay, so now if we are just trying to draw the diagram of the negative edge triggered flip-flop, it would look something like this. Okay, there it goes. Okay, there's the J and the K inputs. Okay, and there at the clock input we would have a bubble in this case. Okay, so now this bubble indicates the presence of a NOT gate at the clock input to this flip-flop. So this is basically the diagram of the negative edge triggered JK flip-flop. Okay, so now if we just quickly move on to its truth table. Okay, let's move on to the truth table. So we'll have the following heads. Okay, I'll use a different color in this one. All right, so there goes the clock, the J, K inputs, and the Q and Q bar outputs. Okay, so if we just let's say assume that the previous state of this flip-flop was a 0, 1 in this case, and then we just apply an input to the JK terminals as, let's say, 1 and 0. We'd observe no change. But why was this so? It's because we did not apply any clock signal. Okay, so now if we just apply a clock signal at the input to the clock terminal, then we would see that the output changes states. Okay, the output would become 1 and 0, and then if we just reverse the conditions at the input to something like this, okay, at the presence of the clock signal, okay, then the output would change again to the state that was previously held by the flip-flop. Okay, so the transitions at the output, or rather the output changes that take place, okay, all of them take place at the arrival of the positive, or rather the rising edge of the clock pulses. Okay, so now we see that whenever the J is kept at logic 1 level and K at logic 0 level, the Q output switches to logic 1 level. Okay, and now when the J terminal is kept at logic 0 level and K to logic 1 level, the Q output switches to logic 0 level, and Q bar correspondingly changes states depending upon the conditions on the Q output. Okay, so here we see the various conditions right over here, and now if at the presence of the clock pulses, if we apply 0 input signal, or rather logic 0 input to both J and K inputs, okay, then the conditions at the output would just remain the same, and here there would be no change. And similar things would happen in the absence of the, in case of the absence of the clock pulses. So here also we would have no change. Okay, so again, now the speciality of this flip-flop is that it's state where both the J and K inputs could hold a logic 1 signal. Now when this would happen, then the output over here, that's the Q output, would begin to toggle. That is, here if Q remains previously at, let's say, logic 0 state, upon the application of logic 1 signal to both the J and K inputs in the presence of the clock input, the Q would change to logic 1 level from the logic 0 level if this would be its previous state, and Q bar would change to logic 0 level correspondingly. And then if we just maintain the same inputs, then the arrival of the next clock pulse would witness the change to something like this. Okay, the output would just begin to toggle from logic 1 level to logic 0 level and vice versa. So here this state is referred to as the toggle state of the JK flip-flop. Okay, so having said that, if we just sum up all that was needed for the JK flip-flop, and now we would show you about 2 other flip-flops, okay, that could be derived from the JK flip-flops as well. Okay, so introducing the D flip-flop. Okay, there you go. In case of the D flip-flop, okay, or rather let me just first show you the D flip-flop. Okay, fine. So if this is a, or rather let me just show you the T flip-flop in the beginning, so that would be much more easier to understand. Okay, so if this is the T flip-flop, okay, I'll come to the D flip-flop later, don't get disappointed. Okay, so the T flip-flop can be derived from a JK flip-flop in somewhat this fashion. Okay, so if this is the input of a JK, or rather this is the diagram, or the logic diagram of the JK flip-flop, okay, and here's the clock input. And now if we just try and connect the J and K inputs of this JK flip-flop together, okay, then what we get is the T flip-flop, whose logic diagram would appear something like this. Okay, there you go, Q and the Q bar outputs, and here we have a single input, that is T. Okay, so now depending upon and here would be the clock signal also, I just forgot about that. Okay, so now if we just quickly move on to its truth table, okay, so we'll have the following heads. Here's the clock, the T, the Q, and the Q bar outputs. Okay, so if we just assume that the flip-flop output is at the state, let's say at the state 0 and 1, okay, in this case, okay, let's just use a different color over here, 0 and 1, okay, then upon the application of a logic 0 signal at T, okay, if we just gonna apply a logic 0 signal at T, even in the presence of the clock input, the outputs would not change at all. Okay, so here also the outputs would remain just the same. Okay, so we see that here's no change at the outputs basically. Okay, so since by applying a 0 0 signal to both the J and K inputs, there is no change at the output stage of a JK flip-flop, and so since this T flip-flop is being derived from the JK flip-flop, it exhibits the same sort of phenomena as J and K inputs over here are tied together. Okay, so that's the basic reason of why this phenomena occurs. And now if let's say we change the input signal at T input to logic 1 level, then during this case the flip-flop begins to toggle. Okay, so if this was the previous state of the Q and Q bar outputs, then it would change, then Q output would change to the logic 1 level and Q bar to logic 0, and if we just maintain this logic 1 input at the T terminal, then Q again would toggle back to 0, logic 0 level, and Q bar to logic 1 level. So here what we find is that this is the toggle state of this flip-flop. So this is basically, the T flip-flop is basically, useful for the toggling function. Okay, so now having said that about the T flip-flop, if we just move on to the next type of flip-flop that could be derived from the JK flip-flop. So here we have the D flip-flop that I was going to tell you about previously. So if we just try and consider this box as the logic diagram of a JK flip-flop, which I am doing to just save a bit on the time and space. Okay, so here's the JK flip-flop. Okay, and there's the clock input. In all the cases we just assume the use of a positive edge triggered JK flip-flop for simplicity. And now if we just try and connect a NOT gate from the J input to the K input, then what we get here is a D flip-flop. So this basically transforms to a logic diagram that would look something like this. Okay, there's the Q and the Q bar outputs, the clock signal or the clock input, okay, and here's the D input terminal. Okay, so now the D flip-flop could also be derived from SR flip-flops as well. So if you just take, for example, this to be the logic diagram of an SR flip-flop, okay, this being the clock input, sorry, okay, there it is. So this being the clock input, if we just try and connect a NOT gate in the similar fashion as done in the case of this the JK flip-flop, okay, so what we get is the D flip-flop right over here. So this thing is just similar to what we saw in the case of the JK flip-flop being converted to a D flip-flop as well. So this is the D flip-flop, okay, and previously this would be the T flip-flop, okay, being derived from both being derived from the JK and SR flip-flops as well. So here if we just quickly move on to the truth table of the D flip-flop, it looks something like this. So here we have 4 inputs, or rather 4 heads, the clock, the D input, and the Q and Q bar outputs. So if we just let me just change the color for a moment. Okay, in case of a D flip-flop, if we just let's say assume that the Q and Q bar states would be, let's say, 1 and 0. Okay, now if I just apply a logic 0 signal at D, okay, in the presence of the clock signal, then the output at Q would be just reset, or rather Q would just switch back from the logic 1 state to the logic 0 state, and Q bar would change accordingly from 0 to 1 state. Okay, so if I maintain the output, or rather the input at D to logic 0 level, then also the Q would remain at logic 0 signal without any kind of change. Okay, so that's how this process basically occurs. So now on the contrary, if I just put the D input at a logic 1 level, okay, then if this would be the previous state of our D flip-flop, then it would just be set in this case. Okay, now the output at Q would be just changed from the logic 0 level to the logic 1 level, and Q bar would change in the same manner. Okay, and if we just continue maintaining this sort of input at the D, okay, then Q remains at the logic 1 level, okay, as long as the inputs at D do not change. Okay, so this particular area is referred to as the reset state of the D flip-flop, and this is referred to as the set state, where Q changes from 0 to 1. Okay, So having said that, we just come to the end of our tutorial discussion on the various types of clocked and edge triggered flip-flops. Okay, so I hope you have enjoyed our tutorial, and don't forget to watch our next tutorial on digital electronics. So till then, it's goodbye for now, and thank you.